Welcome. This is ELTE131, which is Machine Controls 1. Specifically, this is Module B, where we'll be talking about transformers and power systems. During this lecture, you would have downloaded this PowerPoint. You would have clicked right here to launch the video that you're listening to right now. You're occasionally going to have to stop this video and then go back to the PowerPoint and click on some additional links when I prompt you during this presentation. You're going to fill out a video lecture worksheet that kind of follows this lecture, and then you're going to complete the interactive lecture activities. You'll turn that in to the instructor when you're done. We're going to be doing a little bit of a interactive lecture. We're going to be taking a look at transformers. So you're going to need a fluke, a center tap transformer, and a dual coil transformer, and some banana jack leads. The lecture B, our outcomes are going to be is we're going to talk about how is energy conversion used to produce electrical energy. What's the difference between single and three-phase electricity? What's the difference between Y and delta connections? Why is three-phase preferred to single-phase power? How are voltmeters installed in the circuit? What is the scientific principle that allows transformers to work? What is the purpose of equipment grounding and how is it implemented in industrial environment? So in the prior unit, week 1 or module 1, we learned a variety of different things. One of the key points was that an open switch has theoretical resistance being infinite. There's no flow through it. And when you close the switch, you got a theoretical resistance of 0, and current would flow through it very well. Now remember that that's theoretical. You might measure something other than 0 on a closed switch. There might be some resistance in the switch or the leads or something leading up to that. In the week 1 or module 1 review lab, this was basically a review of Ohm's law, and we did series and parallel circuits. And we learned that ammeters are added in series, and you kind of install them as part of the circuit as you're going. We learned that voltmeters are added in parallel, and basically when you get your circuit all done and built and working, you can then just add the voltmeters parallel to the loads or parallel to the source. Add those after the fact so it doesn't confuse you. A big thing that we learned that we'll be talking about more here is that adding resistance in series increases the resistance, which decreases the current flow in a circuit for a given voltage. And that when we add resistance in parallel, it kind of did opposite. It decreases the resistance and decreases the current flow in a circuit for a given voltage. So that was the effect of adding resistance in series and parallel. We did an analog scale, and it was a good idea just to familiarize ourselves. There was a few kind of difficult ones here. One we want to look at was the reading here for resistance. So this is times 10,000. Resistance we would read just across the top here. So it looked like this was about 120. 120 times 10,000 was going to give us 1.2 million ohms. Or we had to change that into k ohms for right here. Okay, so we had 1200 k ohms. And then this one was a hard one because we were reading MA, and it was on a 500. When you come down here, you didn't see the 500, and you had to then multiply or use a factor here. So if we went on right on the 250 right here, it looks like this is about halfway between 200 and 250, which was 225, but we had to then multiply it by 2 because we were on the 500 scale, and so it was about 450 MA, okay? So once again, 450 MA, and this was about 1200 k ohms. Series and parallel circuits. So what we want to do is take a look, just review. We're going to take a 20 volt circuit and take a look at what it looks like with a 2 ohm resistor. Then we're going to create a series circuit, and then we're going to create a parallel. And you're going to fill this out in your lecture worksheet. So you want to go ahead and stop this video and you want to go back to the PowerPoint, and you want to click on the link here and launch this video and fill out your lecture worksheet. Okay, now that you're done with that, we want to talk a little bit about high voltage. So the LCC ELTE courses on our power supplies primarily use 120 VAC on our lab volt supplies and 280 volts three-phase. That's what most of the lab activities and many of the courses are. There's a couple of courses where we demonstrate higher voltages. In the 131 here, we can show you some higher voltage. In the motors class, you'll see some higher voltage up to 480 VAC. This is pretty dangerous. That's why we don't work regularly with it. The 208 three-phase is also very dangerous as is 120. You just got to be very careful. Some of the courses and the controls in the PLCs, for example, utilize 24 VDC. And in the 131 here, we also have a brief unit with 24 VDC. And so what we're going to do is introduce the YouTube transformer and power fundamentals and talk about the different voltages. So once again, if you want to stop the video here, you can go to the PowerPoint and click this link here to take a video of what I'm talking about very high voltages. So first of all, when you talk about electrical induction, induction works on the principles of electromagnetism to create voltage to produce a current. And so basically what this says, and I think you remember back from your primary school days, that if you have a coil of wire and you move a magnet around that coil of wire, well then you get current, or you get potential voltage that can create current. Okay, so wave a magnet around a coil and you get current. And the opposite is kind of true, and that's definitely what you learned in your primary school days, is that if you were to take current and you were to, remember you wrapped it around a piece of iron or something like that, and you ran current through a coil, then you get a magnet. Okay, so magnet makes current if you've got a coil, and then magnet makes current, and current makes magnet. So that's the way, that's the summary of induction, I guess. And we'll talk a lot more about it here in just a minute. Transformers. So transformers are used to increase or decrease voltage levels in order to transmit power. There's a lot of different voltage levels out there, and depending on what you're plugging into or what you're doing, you may need a certain voltage level. You get those voltage levels with transformers. So if you get high voltage generation or transmission, you can maybe talking 765,000 volts, I guess, or higher. But electricity it's generated and transmitted at the highest levels of very high voltage, and that's what that video showed with the power lines, very high voltage. You're going to have high voltage power transmission lines, big towers. A lot of those will run 66,000 to 345,000 volts. It's very dangerous. You wouldn't want any of this voltage in your house, because as you saw in the video, it kind of arcs itself. It's very dangerous. Sub-transmission, then they break that down and they transmit from 33,000 to 66,000, and they distribute it at less than 33,000. Still very high voltage. You wouldn't want this, okay? But distribution even goes less until when you finally get out on the telephone poles, it gets less and less. And then coming into a facility, it might come in 11,200 or something. And then they got to transform it down, because a lot of industrial is 208 to 480 volts. Also in your house, you're going to have residential, which is 120 to 240 volts. I was throwing some voltage levels out there. There's all different types of voltage levels, just depending on how they're transmitting it, and distributing it, and using it, okay? And so you need a lot of different transformers to get these different voltage levels. So going back to induction, and what I was talking about a minute ago, a transformer works on the principle of mutual induction. So when you have a transformer, you're going to have two coils. You're going to have a primary coil and a secondary coil, okay? The purpose of the first coil is to make a magnetic field. And how do you make a magnetic field? You take voltage and you run current through it. And we just talked about that a minute ago. You learned that in primary school, that you get a magnet, okay? This needs to be an alternating magnetic or alternating voltage source. So you get alternating current. So the current kind of flows left to right and the magnet expands. And then it changes direction this way, and then the magnetic field contracts and expands the other way. And then it switches directions and it contracts and expands, contracts and expands. So this over here is kind of like waving a magnet back and forth. You know, otherwise you'd have to have a permanent magnet and just keep waving it left and right, left and right, left and right like that, a permanent magnet. But we want this coil to create an alternating magnetic field, and that's the way that that works. So on the secondary side, we have a coil of wire, and as we talked about a couple slides ago, this magnet keeps creating this magnetic field. It's alternating, and so that magnetic field kind of waves in front of this. So it waves left and right, left and right, left and right. So it's kind of going back and forth. And what that does is that creates alternating current in the second coil, which then is potential and can be used to create current. Okay, so mutual induction. To say it again, current through a coil creates a magnetic field, and on the other side, a magnetic field by a coil creates current. So they're just kind of opposite of each other. Okay, that's called mutual inductance. Transformers either can step up or step down the voltage. in the controls, the machine controls, we're often using a transformer to step it down because we went back and we looked at all those high voltage levels a little while ago that are coming into a facility, and we want to step those down and we want to use them. Okay, and so we want to take a look at the input side of the transformer, what is called the primary. So typically, we're talking about the primary being a higher voltage. The output side is called the secondary, and the secondary is where we're getting a lower voltage. They're showing a magnetic core here because going back to your primary school, when we were making that electromagnet, when you put a nail, I think what we did is we took a nail and we put a coil of wire around it, and you notice that the iron or the core made it a much better magnet. So you're going to have a magnetic core here, transformer core. Now, the turns ratio dictates how it decreases or increases, all right? If the primary here has more turns than the secondary, then it will step it down. And if the secondary has more turns than the primary, it will step it up, okay? And so we're going to talk about this just a little bit more. Remember, we talked about what happens when you put items in series, what happens to current, and when you put them in parallel. So that's what we're going to talk about. But remember that if there's more turns on the primary than there is on the secondary, it will step it down. Okay. You want to stop here and watch this transformer video, and then come back to the PowerPoint. So power in and power out equals power out on a transformer. That means that the power on the primary is equal to the power on the secondary. It doesn't get lost. The primary and the secondary are isolated from one another. There's conductors on the primary and there's conductors on the secondary, but they don't touch each other. The only interaction that they have is through a magnetic field. Okay, so nothing's lost. The power in equals the power out. So the power is the voltage times the current. So that's often referred to as power or watts or VI. VI you're going to hear a lot, which is voltage times current. So VI in has to equal VI out. And so an example here is we have a transformer supplied by 480 VAC. So that is my primary voltage. And I'm going to move that right here. So that's V. That's my voltage coming in. And it's drawing 12 amps on the primary side. So that is my current here on the primary side. So on the left of this equal side, I have a VI of 480 times 12. Okay? The transformer has a turns ratio of 4 to 1. 4 to 1, that means that the primary has more turns than the secondary. That means that we are stepping the voltage down. And we are stepping the voltage down as a ratio of 4 to 1. Okay, because the turns ratio gives you the step. So 4 to 1. So if we have 480 here, the ratio of 4 to 1 is 120 on the secondary. because 120 times 4 is 480. So this is a step down, and it stepped it down by a factor of 4, 120 volts. So then we want to know what is the amperage on this side. Well, remember, power in equals power out. So 480 times 12 has to be equal to 120 times X, okay? And so what do we have? Well, if we cut the voltage by a quarter, doesn't that mean that we have to multiply the amps by the reciprocal of that times 4? So one more time, the voltage gets cut down to 1/4, and therefore we have to take the amps and we have to multiply it by 4. So 48. So if you do it on your calculator, you'll see that 480 times 12, get that number, and you'll see it equals to 120 times 48 amps. So notice that by stepping down the voltage, we increase the amperage quite a bit on the secondary, okay? And we talked we'll talk a little bit about power transmission, of why it's beneficial to transmit power at higher voltage, because you can run lower amps for the same amount of power. Okay? Now, a control transformer is what you're going to see in this course quite a bit, and you'll see it in controls. The purpose of a control transformer is to take three-phase, either 480 or 240, and you want to step it down to 120, because 120 is kind of a common control voltage. Most things that you have in this world kind of plug into 120. That's what residential is, and there's a lot of pilot lights and a lot of devices and everything that operate at 120. So when we get this really high voltage 240 or 483 phase, how do we get 120 something useful? So here's what a control transformer looks like, the depiction of it, okay? And there's two pictures here, remember, or excuse me, even though there's three pictures here, we're looking at these two up here as how to apply to this coil, okay? So this first one right here is telling me if I want to get, about 230, and I want to get it to about 115. That's a 2 to 1 step down, and this tells me how to wire it here. This one here is about 460 to 115. Notice that's a 4 to 1 step down, okay? So the 4 to 1 step down is the easiest to apply to this. So if you look at your transformer, you're going to see that you're going to have 4, 1, 2, 3, 4 connection points on the primary. You're going to have X1, X2 on the secondary. All right, so how do you make these connections? Well, according to this, between H1 you would plug in, a hot wire, and at H4 here you would plug in your neutral. So there's your voltage between H1 and H4, and that's what it's showing here at 460. And then we have to do a jumper right here across H2 to H3. And so basically we've taken this resistor, or this load, and we've ran it in series with this load, okay? And so we've made this coil of wire, we've increased the turns on it quite a bit. So going back just to the start of this, when we were reviewing, we talked about that when you put loads in series, you get more resistance and less current. So that once we jumper right here, we're going to get less current through here, okay? And so that is going to allow me to step that down from 4 to 1, okay? For parallel, you're going to apparently run your power once again to H1 and H4, so you would plug in, your hot here and your neutral here. And then you would then plug in your H1 to H3. So H1, you'd get jumper to H3 right here. You'd have to connect these, and then you would do H3 to H4. Okay, and so we learned that your resistance will go down when you put in parallel, which will cause your current to come up. Okay, so we'll continue to talk about the way that this gets hooked up. Here's a control transformer video right here that you want to stop and pause and watch how I hook up a transformer and how we get different voltage, the different voltage out here. But you want to remember that when you put this in series, you're increasing the turns, you're increasing the resistance, and and that is going to decrease your amps, right? And then if you put them in parallel, remember how that affects your current, and then how it's going to affect your coil here. So watch that video, and then we'll come back and keep watching here. The last one was industrial control transformer. We explained how that works. The other type of transformer we have is going to be called a center tap transformer. In the lab volt, we have a center tap transformer here. And what this one is it's got different coils in it, a primary and a secondary. This is actually the primary over here, and this would be the secondary, the way that we use it. And there's no jumpers on, well, there's some jumpers here, but it's internally jumped on the coil here. So there's just a single coil, and they've pulled off different connection points to access this coil, okay? And so the way that we're using it, let's say we wanted to get a certain step, we let's say 208 is what we have for three-phase. Well, we would run, pretty simple, we would run 3 to the hot, to the neutral, and we would run 6 to the hot. And so then it passes through this entire coil here, and then it's made to step it down to 120. And then here at 1 and 2, that we have our control voltage. But you can get different voltages here. So if you, for some reason, had one, if you wanted to use it the other way, and you ran 120 on this side, well, on this side, you could get 208. Or if you connected between 5 and 6, you could get 208 minus 180. Notice there's not many coils here. You could get 28 volts. Or between 4 and 6, you could get 104 volts. Or between 4 and 5, if you subtract these right here, you could get 76 volts. Or you could get 180 volts. There's a lot of different options that you could get depending on if you ran 120 on this side as your primary, and then you picked off your points here. There's different voltage levels, and you don't have to do any jumpering on the coil. You just have to pick the points of where you want to connect to. So that is a center tap transformer, a little bit different than that control transformer. For electrical generation, it uses the principle of electromagnetic induction as well, and we talked about what happens if you move a magnet by a coil. All right. So electricity is generated by moving a magnet, a permanent magnet or electromagnet near a coil. So what's shown here is a north-south magnet that is spinning. Okay. And so as this magnet, this north magnet, comes up close to this coil, that what does it do? It is going to create potential, or cause, if you have a load here, cause current to flow in there. And then as this north goes away from that coil, it's going to start coming around here, and then it's going to go to the south right here, and then it's going to once again as it gets closer and closer, it starts creating potential, and then it keeps spinning around here. And then this south is going to do the opposite, because it creates a magnetic field in the opposite direction. Okay, which is shown here, that you end up changing your current flow from left to right, or from right to left, as this spins. Okay, and we'll talk about the sine wave here in just a little bit. But that's the premise of electrical generation, is that you want to repeatedly wave this magnet by a coil, okay, a permanent magnet or electromagnet by a coil, and then you'll generate potential. And so a lot of times they'll use like a hydroelectric dam or something, or a windmill, or a gas turbine or something to spin this very quickly, and these magnets get spun by the coil here. So you want to take a second here and watch this generation architecture video. Shows you different type of alternators, whether you have permanent magnet stators or rotors. So take a look at that. So single phase electricity is depicted by a sine wave. And so our amplitude here is 120 volts. So it goes from 0, in our case, is 120 is our residential. It would take an amplitude up to positive 120 to minus 120 to positive 120 to minus 120. And it alternates like this, because we have alternating electricity. And because we were using a magnet that was continually going around north, south, north, south, north, south, you end up as shown in that video, you end up with the current like this. So how fast does this change? The time period here is 60 hertz. So it switches direction every 1/60th of a second. Okay, so that is an example of the sine wave and how the sine wave represents single phase electricity. There's a little video here that shows that as the magnetic field is broken, as the magnet um, and the coil approach each other, the peak amplitude is reached, and as the magnet moves away, it gets less and less and less, and then until it gets the opposite coil, and it increases until it gets very close to it, and then it decreases. So take a minute and watch the amplitude video here and see how the magnet causes this to increase and then decrease as it rotates. Okay, so on 240 VAC single phase, this is what you have in your house. You have a 120 240 single phase system, which means that you have high voltage 240 VAC in your house, and maybe some of the bigger things in your house might be run by this, like maybe your air conditioner or your well, if you have an electric dryer, things like that is run by 240. But all your plugs and outlets are 120 VAC, so this is what you have in your house. And the way that this is generated is that there are two single phase generators that are 180 degrees out of phase, so they're opposite of each other. Okay, so if I take a look at my household voltage here, I have phase 1 and phase 2. It's not called two phase. Um, you know, it sometimes is referred a little bit as two phase, but that's really not that common to call it two phase. It's be referred to as a 120 240 system. So we have the first phase that we just talked about and we saw in our videos, and that's going from plus 120 to minus 120, plus 120 to minus 120. And so if I want 120 volts in my house because I want to plug something in like a blender or a computer or anything like that, well, between the 0 here, which would be the white wire in your house, the neutral wire, and the first phase, let's say, is the black wire. Between the black and the white wire, there's 120 volts, and that's what's showing here. The neutral being the white, line 1 being black, you see we have 120 volts. But now we have a red wire that's opposite of this. So when this one's hitting plus 120, this one's hitting minus 120. Okay? And so if I wanted 120 on another outlet, I could run it from the white wire to the red wire. So from the white neutral here to the line 2, which would be red, I could get 120. But if I wanted 240 volts, what I could do is I could go from the black wire to the red wire. And so instead of just coming to 0, I keep going all the way up to 120. So you add those two together, and you get 240 volts. You take phase 1 minus phase 2 is what it is. So 120 minus a negative 120, that becomes plus 240 across here. And that's what's showing here between the black wire and the red wire. You have 240 volts. So that's how your house works. And so these were two 120s, but they were generated 180 degrees apart. That three-phase, I'll have to fix this a little bit. I'm still talking about the old one. What three-phase is doing is has three single-phase lines, okay? And these are all generated 120 degrees apart. So, you got voltage 1. This one starts rolling up and it starts increasing, but then this one is 120 degrees apart. So this doesn't get to 0. When this one gets to 0, this one has already reached the peak and started to come back down. And when then the next one, voltage 3 gets to 0, then voltage 1 is coming down and voltage 3 is starting to come down. Okay, so these are all 120 degrees apart the way that they're generated. And so you have a variety of different potentials here. You have voltage 1 to 0 to your neutral right there. Okay, and so If this was 120 generation, that'd be 120, right? And if you have voltage 2 to 0 and you have voltage 3 to the neutral, those are all voltage potentials. You also have voltage 1, the difference between voltage 1 and voltage 2 for a given time. So it looks like in this case, this one at the peak here, this is at 120, and if you come down here, voltage 2 hits somewhere in here about, not quite halfway. So you would add those two together, and then you would get at this point, let's say 208 volts. Okay, if you added them together, you have voltage 1 to voltage 2, voltage 2 to voltage 3, and voltage 1 to voltage 3. You could touch your multimeter across any of those for the different voltages. Okay, like I said, I'll touch that up. Three-phase, once again, I got to touch that description up. But the way your 208 volts using three-phase, that's what we have going here. Our power supplies have 120 volt single phase generation. We have 3 of these. I'm only showing you 2 of them right here, but there is a third one running in here. Okay, but we're just going to take a look at 2. And these are 120 degrees apart. Okay, so we have phase 1 running 120 and phase 2 running 120, but they're slightly delayed to each other. Okay, and so when you subtract the phase 1 from the other phase, that gives you your total potential. All right. So if you take this point right here, this one looks like it's about 60 right here, right? I'm going to 0, 1, 20, about 60. So you're taking phase 1, which is 60, minus phase 2, which is about 60, because that's where they're crossing. And sure enough, right here, where the black is, you got 0 volts. 60 minus 60 is 0. But as phase 1 is going up, phase 2 is going down. And then this black line here is the subtraction of the 2. So you notice that once you get here, the difference between them is greater than 120. And sure enough, if you come up here, it's getting higher and higher and higher, and it reaches 208. So that is the subtraction of the 2 phases. And so, like I said, this would be phase 1 to phase 2. There's another one of these curves that's phase 1 to phase 3. And there's another final curve that's phase 2 to phase 3. So we have 3 208 different taps that we can get right here. Okay, we can get A to B, A to C, and B to C will give you all 208s. And we have the neutral wire, that's a 0. Then we can get A to neutral, B to neutral, and C to neutral, and those are my 120s. Okay, so once again, I will clean this up there, but that's the 3-phase. Now, my motor operation here's a very simple explanation of a motor operation, because 3-phase is great for running motors. Okay, it's essentially kind of the opposite of a generator, in a very simple way. So for a generator, what we did is we rotated this magnet by these coils, and then we generated potential. And as the magnet end got closer and closer and closer until it lined up perfectly, then that's when we had the peak, and then when it walked away, it got less and less and less, and that's why we ended up with a sine wave. It peaked out and went lower, then it went to the next one. Okay. Well, a motor, you can imagine, kind of works the opposite of that. So if we were to take this coil right here, and we were to run a current through it, we could generate a magnet. And if this was a south magnet, if this was a north magnet, we know that opposites attract and likes repel. So if this was north and this was north, well, this north is going to want to move, so it will rotate towards this way. All right. And then this red one, because it's a little bit delayed, well, just a little bit later down the line, this will become a north. And then the green's delayed, so this will become a north, and north, and north, and north, and north. So this is going to keep getting pushed away the entire time. Okay. But now the opposite of it, notice when this one, like we said, was becoming a north magnet, because that's the flow of it, this one was becoming a south magnet, or a north magnet, sorry. We had north magnet here, north magnet here. And so these norths repel, but these north-souths attract. So the whole time that these are going around pushing this north away, These are just ahead of it, and these are all north, which cause it to attract the south. So this gets attracted as it goes around, and this gets repelled as it goes around. So that's kind of a quick uh, explanation of how a motor works. It's kind of the opposite of a generator. For power comparison, you're going to have single phase in your home, just a little bit safer. And in the simplest sense, you're going to need one hot wire and one neutral wire producing power. And remember, power is VI, voltage times current. Okay, that's single phase, 2 wires. And then we learned on 3 phase, you're kind of going to have 3 hot wires, and these hot wires are going to be 120 degrees apart, and you're going to have a potential across those. From phase 1 to phase 2, phase 1 to phase 3, and phase 2 to phase 3. Those are my 3 potentials across those. So because we have 3 different potentials, we have 3 times the power. All right. So if we had 10 watts, for example, in a single phase, we had power consumption of 10 watts. We need 2 wires. We need the hot and the neutral. So we need 2 conductors to do 10 watts. Now, on 3 phase, we have 3 times the power because we have those 3 phases. We just don't have the one phase. Once again, we have phase 1, phase 2, phase 1, phase 3, and phase 2, phase 3. So we're actually doing 3 times the power. We're doing 30 watts, and we only need 3 conductors. Well, wait a minute, you say. 10 times 3 is 30, so 2 times 3 is 6. I don't need 6 conductors, though. I only need 3. I need a conductor for phase 1, a conductor for phase 2, and a conductor for phase 3. So therefore, what does that mean? I get 3 times the power, but I don't have 3 times the conductors. I don't have 6 conductors. I only have 1.5 times the conductors. So that's why the power is good to generate and transfer power using the 3-phase like this. 3 times the power for 1.5 times the conductors. Y connections. So when you're utilizing a transformer and motor connections, you can connect this power in different combinations in order to get different voltages, okay, and different performance. So this is called a Y or a star. It's kind of a common connection. And what you would have would be phase 1, phase 2, phase 3, and this one's got a neutral, okay? And so if you were to take, let's say you had a motor in it, and it had these motor coils. I'm going to go back to this motor real quick. Here's the orange coils, the red coils, and the green coils, okay? So, if you were to connect them like this, you're going to get different characteristics depending on what kind of operation you want. So in this case, these coils are connected in a Y, and you can tell that this first coil right here ends up in series between this line and this line. Line 1 and 2, let's say, and then between line 1 and line 3, I've also got a series connection here, and I've also got then a final series connection between line 2 and line 3. So that's why we're talking about what was happening earlier. What happens when you put resistance in series? You're going to get more resistance, right? And then you're going to get less current flow. Okay. And a delta connection. Is another way to connect them. These are connected end to end. So you have your phase 1, your line 1, line 2, line 3. And so between line 1 and line 2, there's no series. It's just single coil. Okay. But you do have some other paths here. This is parallel, so you can come to this coil and then go to this coil and then to line. Okay. So in a delta connection, you've got parallel right here. So we talked about that when you get parallel, your resistance decreases, and then your current is going to increase. All right. So that goes back to, once again, the way that we were talking about the transformers and the relationship there, and you really want to understand that. You have a lot of different voltages that we might use. 208, 277, 480. These are some common voltages and some common connections that you'll get with this between the Ys and the deltas. Okay, and your line voltage is what is your difference between line 1 and line 2 and line 2 and line 3 and line 1 and line 3. Those are the three. So if you wanted to get 208, you could connect these as a Y and you would get 208. And that's what we were showing right there. 120, you could connect here's a 120 to neutral, here's a 120 to neutral, and here's a 120 to neutral. And that would give us from line to line 208. Okay? And so if you connect those up as a delta, you're going to get different voltages here, depending on your line to neutral. Okay. The your book has a bunch of connections, a handout here that shows deltas and Ys and what your line is, whether you have 240 coming in or 120, and it lists what you could get for your voltages. Okay, and you're going to want to have to memorize these. What is a delta Y? What is a corner grounded delta? There's a corner ground. What's it look like and what voltages are available. So we'll take a look at that handout and you'll definitely want to memorize it. Okay. So just in review, we started up here with reviewing our lab, and the big thing that we learned was that adding resistance in series increases the resistance and decreases the current flow. So we took this principle, decreases the current flow, and we applied it to transformers here. That what happens when you put these in series, okay? And then we learned about, from the previous lab, we just reviewed that when you put in parallel, you decrease the overall resistance and you increase the current flow. And then we applied that to, a transformer here. What if you jumpered H1 to H3 and H2 to H4? How is that going to affect the transformer? Okay. And then we talked about what that all applies to how you connect something with Y, whether it ends up being a series connection here. These would all be series paths, line to line. Or if you end up with a delta, you're going to end up with parallel loads here between your lines. And that is going to give you different voltage characteristics depending on what device you hook up and how your transformer is hooked up. So that's a pretty quick description of that. The reading and the homework really goes over how those relationships work, and you'll definitely want to understand and memorize the voltages that are available with different transformers. So at this point, you're going to complete your lecture video worksheet, and you're going to turn that in, and the lab instructor will let you know